The following has been developed by state and provincial agencies in association with the Agency for Instructional Technology. Together, serving education.
I never thought there'd be so many parts. And look at all these screws. I hope we get it up before they come home.
Earl, don't worry. There's no big trick about putting together a swing set.
I bet Pammy's really gonna be surprised. She never expected anything like this for her birthday.
Yeah, she's really gonna love it.
Hey, what are you doing, Mark?
Screwing a leg together. What does it look like?
But shouldn't you follow the diagram?
I don't need that. I know how it goes.
But Dad always follows the diagram when he puts things together. Remember when we got that barbecue grill last summer?
Look, I don't have time to mess around with the diagram. Mom said they'd be back by 3. Hey, are you just gonna stand there or what? Start screwing together another leg.
Diagrams. Why do we need them? Well, diagrams can show us how to go about a particular task in a clear, easy-to-follow manner. Diagrams can also show us how something works, or illustrate the relationship between two or more things. And diagrams can save us from making some big mistakes.
Let's see. Maybe if we unscrew this piece and put this one here, or maybe we can move this whole section.
Well, when you don't use a diagram, you can construct some pretty original creations. A little too original. The swing set would have looked more like a swing set if Mark had used the diagram. But have you ever thought about other things diagrams can do, other ways they can help us? Diagrams can give us a clear visual image of how something works, like this diagram of the digestive system. Diagrams can also illustrate the steps in a complicated process, like how a steam engine works. Diagrams can also help us get from one place to another. An architect's blueprint is another type of diagram. Without it, the carpenters wouldn't know where to put the walls. This is a diagram of a time-distance problem. In the example here, the bus is going 30 kilometers an hour, and the train is going 45 kilometers per hour. Now, assuming neither had to stop, how much sooner would the train arrive in a town 200 kilometers away? The diagram helps you find the answer. Each distance line is divided into hours, showing the distance traveled in that time. So you can see it takes the bus 3 hours to go as far as the train traveled in only 2 hours. To solve the problem, all you have to do is fill out the rest of the diagram. So you see, diagrams aren't just illustrations or charts. They're tools. Tools that explain something we want to know or help us visualize the solution to a problem.
Okay, where do you want to start first?
How about the White Lightning Ride?
Let's go see the big live stage show. My brother says it's great, and it's right near here.
But that doesn't start until noon or something. Isn't there anything we could do now?
Sure, we could go to the puppet show. Or the log ride. You don't want to miss riding the big stern wheeler.
When does it start? This is crazy. We can't just guess or else we miss everything.
Yeah, there's got to be a better way to plan this. Hey, look!
Hey, this is terrific. Now we can tell when all the shows begin and how far away they are.
It looks like the girls might not miss anything after all, thanks to this diagram. A diagram can help you solve all kinds of problems because it can illustrate relationships that could be confusing otherwise, like the relationship here between locations and starting times.
Okay, it's 5 after 10. What are we going to do first?
Well, most of the shows don't start until 11:30 or 12, and the first stern wheeler leaves at 10:30. But look, the powder cake flume is right near here. We could go ride that now and be back here by 10:30 for the sternwheeler ride.
Since the sternwheeler goes around the park every half hour, we'll be back by 11 o'clock. And the first puppet show starts at 11:30. Let's see. The puppet theater is right over here. Oh, we'll have plenty of time to get there.
And that'll give us lots of time to play some games either here or up here in the county fair section.
Super. That'll put us right at the White Lightning roller coaster. We could ride that, then grab lunch at one of the places around Pirates Island. Then we could see the magic show at Troubadour's Roost at 1:30.
Hey, we aren't going to miss the big stage show, are we?
No way. It doesn't start until 2:45. See how close it is? We might even have time to ride the cyclone first.
Big show is over at 3:30. That gives us an hour to shop for souvenirs near the entrance before my mom comes to pick us up at 4:30.
Hey, it works out great.
Yeah, let's go.
Another place where charts are used to determine starting times for activity is the U.S. space program. Starting with the Mercury flights up through the current shuttle program, diagrams have played a major role in the successful completion of our missions. I'm John Japp, a mission planning engineer at NASA's Marshall Space Flight Center in Huntsville, Alabama. Here at Marshall, we're primarily involved in scientific investigations related to spaceflight and the application of space technology to problems on Earth. The development and flight of each space shuttle mission depends heavily on the use of diagrams. This diagram, for example, is used for planning the scientific activities carried out on a Space Lab mission. It shows how we get from the initial requirements of the scientists to the final mission plan, which is used on board by the crew. This plan is the Payload Crew Activity Plan. It details every minute of each crew member's time from liftoff until touchdown. This book is divided into two sections. The first section breaks out the mission into 6-hour time blocks. The top part of the chart details what each crewman is doing and when. The bottom of the chart describes orbital conditions, such as where the vehicle is over the Earth, when the vehicle is in the Earth's shadow, and when the crew can talk to the ground. The second part breaks down the entire mission into 1-hour segments. Where the first part, the 6-hour charts, told the crew what to do, the 1-hour charts tell the crewmen how to do it and include specific scientific procedures. The center column gives orbital conditions, such as when the vehicle is in the Earth's shadow and when the crew can talk to the ground. These columns detail the specific times and tasks to be accomplished during the Space Lab mission. Timing is critical, since each experiment has been assigned a specific time slot during which all of the necessary things, such as electrical power, crew time, correct orbital conditions, and communications are available. Using a flowchart is the best way to make sure that things are completed accurately and on time.
Okay, there are going to be 18 booths in the school carnival, and Mrs. Robbins says it's our job to decide where they all go.
But she says we can't put things that attract big crowds together. And we've got to make the best uses of entrances and exits.
And we're supposed to think of safety.
So where do we start? Let's put the ring toss here, by the door. But wouldn't it be better to put one of the food booths by the door?
I think the ticket booth should go by the door.
You're right. But then where do we put the ring toss and the food booths? And how about the dart throw? Oh, everyone loves that one. Let's put it out here in the middle so everyone can see it.
Are you kidding? And have someone get zapped by a dart?
I'm starting to get confused. Me too. 18 booths, that's a lot to keep straight.
I've got an idea. Let's make a diagram, or better yet, a model.
How do we do that?
John's suggestion to make a model is a good one. A model is like a diagram, only you can move the parts around. Now, by making a model, these kids will have a visual tool to help them plan the carnival. They'll be able to clearly see what works and what doesn't. It won't all be guesswork.
Okay, guys. This is the gym. Entrance, exits.
And these colored shapes stand for all the booths.
We've got 3 blue rectangles for the food booths, and red squares for the different throwing games. We've got colored triangles, rectangles, and circles to stand for all the other booths.
Great. Now what things do we have a definite place for?
The ticket booth.
The orange square. It has to go by the main entrance.
And the table to show the raffle prizes goes right next to it. It's the green rectangle.
These kids are smart. They've kept their model simple and clear, and they've designed it so they can easily readjust the parts until they've got everything the way they want it. Remember, models and diagrams don't have to be great works of art. They're meant to be working tools. No need for unnecessary details.
Let's put the red square for the ring toss here, and the yellow triangle for the fortune teller over here.
Well, it's hard to say without knowing where some of the things will be. You know, the things that are going to attract big crowds.
Right. Let's decide on those first.
That would be the food booths, the blue rectangles, and the puppet show, the yellow circle, and the stage for the raffle drawing, the orange triangle.
I guess we should put those as far apart as possible.
Right. Let's see. The food booth should be here.
As you can see, pieces of paper are a lot easier to move around than carnival booths. Making a model like this can be useful in 3 important ways. It helps you identify your problem, it shows you different possible solutions, and it helps you find the best solution.
And the last red square for the dart throw goes here, so no one will get zapped.
Well, what do you think?
Amazing. Everything is just where it should be.
We did it, guys.
You know, without that model, they'd probably still be debating where to put the ring toss. Think how much time and energy they've saved. And they'll discover their model has another bonus, too. Now, everyone working on the carnival, from the carpenters to the ticket sellers, will have the same clear picture of where everything goes. With a model, there's no confusion, no misunderstandings. Hold on. Haven't we forgotten something? What's happening with Andy and Mark trying to put up that swing set?
Stupid swing set, nothing fits right. Mark, I don't think it's the swing set. I suppose you're blaming me? I just think we'd have better luck if we followed the diagram. Can't we try, please? Okay. Now remember, you promised no shortcuts. Attach bar A to brace B with the medium-sized screw. Everything really does fit together.
MathWorks is a component of the Mathematics for the 80s project and is supported in part by Exxon Education Foundation. This program is produced by the South Carolina Educational Television Network under the supervision of the Agency for Instructional Technology.